Hey, what's up everyone? Welcome to Stoichiometry/Solutions Part 4, which is our last lesson for Stoichiometry/Solutions. And today we're going to do some practice regarding the whole section. So we're going to go over the 2018 local test and the 2020 national test. And we're just going to go through all the questions on the Stoic/Solutions section. And let's just get started. Number one asks, how many oxygen atoms are in 225 grams of O2? All right, let's see what the process for this is going to be. So if we divide the grams over the molar mass, we're going to get number of moles of O2. And if we multiply this number by 6.02 times 10 to the 23rd, we get number of O2 molecules. And since the question asks us how many oxygen atoms are there, we're going to need to multiply by 2. Because in one molecule of O2, we're going to have 2 oxygen molecules. And so multiplying by O2 gives us our answer. And so let's do that. Let's take this process and apply it. So we have 225 grams, and the molar mass is going to be 2 times 16, which is 32. And so that's going to be about, I think, 7.03 moles of O2. And if we multiply by Avogadro's number, we're going to get that we have 4.23 times 10 to the 24th molecules of O2. But if we're trying to find atoms of oxygen, we need to multiply this number by 2. And that's going to equal about 8.47 times 10 to the 24th atoms of oxygen. And what is the answer? There we go. 8.47 times 10 to the 24th. So again, the process was take the number of grams, convert that to number of moles, multiply by Avogadro's number to get molecules of O2, and then multiply by 2 to get number of oxygen atoms. A second question, a 0.3 molar solution of hydrochloric acid is prepared by adding some 1.50 molar hydrochloric acid to a 500 liter volumetric flask and diluting to the mark with deionized water. What volume of 1.50 molar hydrochloric acid must be added? It seems like there's a lot going on in this question, but if you just break it down to the fundamentals, you can see that this is just a dilution question. And so our best friend for dilution questions is our equation, move m1 times v1 equals m2 times v2. So what do we know? We know that our initial molarity is going to be 1.50, and we don't know our initial volume. So we can just leave that as v1. And so m2 is going to be 0.3 m, because that's the concentration that we're trying to get. And our v2 is told right here, a 500 milliliter volumetric flask and diluted to the mark with deionized water. And so what diluted to the mark is just, that means whatever volume that you have right here, you have that volume, and then you just add however much water or whatever is needed to get to the mark. And we know that the mark is 500 milliliters, and so that means 500 milliliters is going to be our ending volume. And that's going to be 500. And so now we can solve for V1. So 1.5 V1 is going to equal 150. And so V1 is 100. So that means what volume of 1.50 molar hydrochloric acid must be added? 100 milliliters. And what is the answer? 100 milliliters. And we got it right. So I guess the big trick in this question was to realize that the second volume here is not additive. You are diluting to the mark, meaning your end volume is going to be whatever that mark is, and we know that mark is 500 milliliters. Third question, copper oxide is reduced to metallic copper by heating in a stream of hydrogen gas. What mass of water is produced when 10 grams copper is formed? So from the question, we know that the reaction is going to be copper oxide, and it's heated in a stream of hydrogen gas. Hydrogen gas is H2, and we know that's going to produce some solid copper and some water. And so if you notice, this equation is not balanced, so let's balance it. We see 2 coppers on this side. That's balanced, and I think, okay, that's all we needed to do. We know that we're gonna produce 10 grams of copper. So how many moles is 10 grams of copper? Well, 10 grams divided by the molar mass of copper. The molar mass of copper is 63.5. So we are going to have 10 divided by 63.5, which is about 0.157 moles of copper, of solid copper. But remember, everything else here is in a 2 to 1 ratio. So if we're trying to find the mass of the water produced, then we know it's that copper and hydrogen are in a 2 to 1 ratio. So if 0.157 moles of copper is produced, then that means that there's going to be 0.0787 moles of water produced. Well, if we know that that's how many moles of water is produced, then we can turn that into the mass by just multiplying by the molar mass of water. And the molar mass of water is 18. And after doing the calculation, you're going to get that it's 1.417 grams of water. And we are correct. So I guess the hard part here was just making the equation here. And the equation really came from the problem itself. We know that copper oxide is going to be treated with hydrogen gas, and then that produces some solid copper and some water, and then we balanced the equation and did some manipulation to get that we're going to produce 1.417 grams of water. Okay, fourth question. The mineral something is 48.41% copper, 19.02% arsenic, and 32.51% sulfur by mass. What is the empirical formula of E? I'm just going to call it E because I don't know how to say that. Okay, so for questions like these, it helps to convert the percentages into mass. So you can assume that the entire mass is 100 grams. We're just assuming. And if it's 48.41 percent copper by mass, that means we have 48.41 grams of copper. We're gonna have 19 point copper. We're gonna have 19.02 grams of arsenic, and we're gonna have 32.57 grams of sulfur. And so, how many moles are each of these? Well, copper has a molar mass of 63.5, so that means we're going to have 48.41 divided by 63.5. We're going to have about 0.76 moles. Arsenic has a molar mass of 74.9, so we are going to have 74.9. We're going to have 0.254 moles. And for sulfur, the molar mass is 32.1. So if we divide that by 32.1, we're gonna have about 2.1. We're gonna have about 1.01 moles. To convert these into empirical formulas, you take the lowest number of moles. So we know arsenic is going to have the lowest number of moles, and we divide the number of moles on all of the three numbers. So what does that mean? We divide this number by 0.254, we divide this number by 254, and we divide this number by 0.254. And this number is going to be about 3, this number is going to be about 1, and this number is going to be about 4. And so what we just did right here is we found the whole number ratios. And this is all an empirical formula is. An empirical formula is just the simplest whole number ratios. And so this 3, 1, and 4 tells us that it's going to be in the form of copper 3, arsenic 1, and sulfur 4. And that is our empirical formula. And we are correct. So for questions like these, you just assume you have a certain mass, and it helps to go with 100 grams because percentage is out of 100, so you don't really need to do much math there. And then convert that to moles and divide the compound with the lowest number of moles, whatever that value is. You divide that by all the three numbers of moles, and you're going to get whole number ratios. And those whole number ratios can act as the ratio for the empirical formula. And that's basically the process for any problem like this. All right, let's move on to problem 5. A 5-gram sample of calcium nitrate, molar mass 164, contaminated with silica, molar mass 60.1, is found to contain 1 gram calcium. What is the mass percent purity of calcium nitrate in the sample? All right, think about what this means. So we have some calcium nitrate, and we know that it's going to be contaminated with silica oxide. We're given that we've detected 1 gram of calcium in the sample. So that means how many moles of calcium is there? The molar mass of calcium is about 40 grams, so we're going to have 0.025 moles of calcium. But you know that in 1 mole of calcium nitrate, you have 1 mole of calcium. So if calcium and calcium nitrate are in a 1-to-1 ratio, if we know that we have 0.025 moles of calcium, then that means we're going to have 0.025 moles of calcium nitrate. We know that we have 0.025 moles, and the molar mass is given right here, 164. And so that means um, it's going to be about 4.1 grams. And we know that the rest of the mass, so we only have 4.1 grams accounted for, but the whole sample is 5 grams. The other mass must come from the silica. And so if we're trying to find the mass percent purity of calcium nitrate, well, we know that the calcium nitrate is 4.1 grams, and the total sample is 5 grams. And so that's going to come out to 82%. And that is our answer. Again, what we did here is we took the calcium and looked at the ratio between calcium and calcium nitrate. And we used the number of moles of calcium and related that to the moles of calcium nitrate. And so that allowed us to find the mass of the calcium nitrate in the sample, and therefore we can take that mass and divide by the total mass to find the mass purity. Okay, last problem of the 2018 local exam. A solution of 20 grams of which hydrated salt dissolved in 200 grams H2O will have the lowest freezing point. So this clearly has to do with our colligative properties, and it's going to be um, based on the Kf value times the molality times the I. We're looking for which one is going to have the highest value. And we know that Kf is going to stay the same for all of them because they're all in water. And so all their Kf values are going to be the same. So what we're really looking for is which sample is going to have the highest molality times I value. All right, so I split up all the 4 choices so that we can look at them one by one. So let's calculate the molality and then the I value. So that the molality here is going to be the number of moles over a kilogram of solvent. So the moles here is going to be 20 grams over the molar mass 250 over 0.2. And that's going to be times the I value of copper sulfate. So copper sulfate is an electrolyte, and so its I value is going to equal 2 because it's going to break up into copper and then sulfate. And so the math here is going to come out to be 0.8. So the M times I of copper sulfate is going to equal 0.8. But I mean, we can't really tell anything about if this is going to be the highest or the lowest without looking at the others as well. Next up is copper sulfate. So our molality is going to equal 20 divided by 263 over 0.2. And its I value is also going to be 2 because it's a strong electrolyte. But already comparing by the fact that the denominator here is lower than the denominator here, we know that nickel sulfate can't be it because the only difference between nickel sulfate and copper sulfate is the fact that nickel sulfate is going to have a lower molar mass, and therefore we already know that this number, whatever number we get here, is going to be lower than copper sulfate. So we don't even need to check nickel sulfate. All right, let's look at the third one, MgSO4. So its molality is going to equal, 20 over 246 over 0.2, and then its I value is going to equal 2 because it's a strong electrolyte. And if we do the math out here, it's going to be about 0.81. So it beats out copper sulfate by just a little. But we need to check the last one to make sure that magnesium sulfate is going to be lowest freezing point. So sodium sulfate is going to have a molality of 20 divided by 286 over 0.2, and but the catch here is that we're going to have a I value of 3. The Van Hout factor becomes 3 because Na2SO4 is a strong electrolyte. It's going to split up into Na plus, and SO4 2 minus. Um, so if we do the math out here, we get that the m times I value here is going to be 1.05. And so clearly, Na2SO4 has the highest value, meaning it's going to have the most freezing point depression, meaning it's going to have the lowest freezing point. And so the answer here is D. And you can't really see it there, but that's the right answer. In hindsight, we could have saved time by obviously canceling out the nickel, but also canceling out the copper sulfate. Because as you can see here, the magnesium sulfate has a lower molar mass, and since no other number changes, then we know that MgSO4 is going to have a higher m times I value than the copper sulfate anyway. So really, the whole competition was between magnesium sulfate and sodium sulfate. Okay, let's start on the 2020 national exam, and I'm gonna start on problem 3 because problem 2 we already did in a previous video, and problem 1 includes some stuff that I haven't taught yet, so I don't want to go there and confuse people. So let's start on problem 3. A sample of 1 gram of which compound contains the greatest number of atoms? So let's go through and calculate the number of atoms for each one of these compounds. So CO, C2H6, C6H6, and Kr. To save us some time, we can realistically cancel out the CO and the Kr because we know that the number of atoms is going to be based on how many atoms are in its chemical formula and how many moles of that compound of that molecule that we have. And CO just if it just doesn't have a lot of atoms within the molecule. If we look at B and C, they have a lot. They have 8 and 12 compared to just 2 in CO, carbon monoxide. And so although we will get a pretty high number of moles, we know that CO and Kr is not going to be able to compete. Kr because, I mean, just look at it. We're going to have the least number of moles in that one, and it has the least number of atoms per molecule. So that Kr just doesn't make sense. And so the only ones that we really have to check are going to be C2H6 and C6H6. So in order to find the number of atoms within the compound, we're going to first need to calculate the number of moles of that compound that we have. And so if we divide 1 gram divided by its molar mass, which is 30, we're going to get the number of moles. And so if we multiply the number of moles by Avogadro's number, we're going to get the number of molecules. So literally how many molecules of C2H6 we're going to have. And then if you multiply by 8, because there's 8 atoms in that molecule, we're going to get the number of atoms. So it's going to be about 1.61 times 10 to the 23rd. That's how many atoms that are going to be in this. And now we can calculate C6H6 and then compare the two values. So we can have a similar approach. 1 divided by the molar mass, which is 78, times the Avogadro's number. And the thing that changes here is going to be the number of atoms per molecule. And so in this one, we had 8. But in this one, we're going to have 12 because we have 6 carbon, 6 hydrogen. That's 12. And let me just do the math out. We get 9.26 times 10 to the 22nd atoms. So I guess they're pretty far apart. C2H6 has a lot more, and so therefore C2H6 or B is the correct answer. And let me check. Yeah, we were right. So we saved a lot of time by not calculating the carbon monoxide and the Kr, and then we just had to calculate the number of atoms of the other two, and it was a pretty simple calculation. And then we just compared the two values to see which one was greater. Okay, let's take a look at problem 4. 200 milliliters of aqueous nitric acid is mixed with 300 milliliters of 0.2 molar MgNO3 solution to give a solution with a nitrate ion concentration of 0.5 molar. What is the concentration of the nitric acid? So in order to solve this question, we're going to need to break down the definition of molarity. So we know that the end molarity is going to be 0.5. And we also know that the end volume is going to be 200 milliliters, 200 milliliters from there, and then 300 milliliters from here. So the end volume is going to be 300 milliliters. So 0.5 molarity tells us we're going to have 0.5 moles per liter. And so how many moles are in 500 milliliters or 0.5 liters? Well, it's going to be 0.25 moles. So we know that at the end, we're going to have 0.25 moles of the nitrate ion. So if we calculate how many moles of nitrate ion are coming from the 300 milliliters of 0.2 molar solution, we can subtract that number, however many moles we got from there, from 25 to get how many moles we're gonna have to get from the 200 milliliter solution. And using that, we can figure out the concentration. So first, let's see how many moles of NO3 is coming from the 300 milliliter solution. Although the problem tells us that we have a zero point 0.2 molar solution, you can't just go off the zero point 0.2 molar because that zero point 0.2 molar is talking about the MgNO3 So in one molecule of that, you're going to have two nitrate ions, meaning the concentration of the nitrate ion is going to be 0.4 molar. It's going to be 2 times that because per one molecule of MgNO3 you're going to have one molecule of nitrate ion. And so this zero point 0.4 tells us that we're going to have 0.4 moles in 1 liter. So how many moles are there in 300 milliliters or 0.3 liters? And so if we do the math, that's going to be about 0.12 moles. What we calculated here is the number of moles coming from this solution. And so that means that if we subtract 0.25, which is our end moles, from the moles we have from here, then that means 1.13 moles of NO3 must come from our 200 milliliter solution. Nitric acid is HNO3, and so we can just keep the molarity here. Whatever molarity of this that we have is going to be the same as the molarity of NO3 that we have because they're in a 1-to-1 ratio. If we assume that the molarity is X, so it's XM, we know that X times 0.2 should equal 0.13. Because X tells us how many moles are going to be in 1 liter, so if you multiply by 0.2, which represents 0.2 liters, aka 200 milliliters, we're going to get that there's going to be 0.13 moles. And so now we just do a bit of manipulation to get that X is going to equal 0.650. So that means our concentration is going to be 0.650 molar. And that is our answer. You can't really see it there because I keep writing over that area, but it's 0.650 molar. So I guess you kind of have to be careful because this looks a lot like a standard dilution question, but you need to solve it some other way because dilution will not cut it as far as I know. And so if you just break down the definition of molarity and you just work off number of moles and the volume, you can reverse engineer the molarity of the initial concentration. Number 5, a student wishes to prepare a solution with a final concentration of Na plus of 0.5 molar and a final concentration of HCO3 minus of 0.1 molar by taking some NaOH and some trona, which is Na2CO3, submerged in some other stuff, and diluting with water to a final volume of 1 liter. How much NaOH and trona are required? Okay, so we know that the final concentration of Na plus is going to be 0.1. Sorry, 0.5. My bad. And by the way, those brackets right there, those brackets imply concentration. And HCO3 minus is going to be 0.1. So we're trying to find the concentration of NaOH and the trona that we need. And so we can just symbolize the moles of NaOH as X, so NaOH, and of the trona, and I don't want to write it out, I'm just going to write trona as Y. So why did we symbolize them as X and Y? Because now we can generalize the moles of Na plus and the moles of HCO3 minus. So in in an X concentration of NaOH, we're going to have an X concentration of Na plus ions produced. And for Y, the number of Na plus ions that are going to be produced are going to be 2 plus 1, which is 3. So 3Y Na plus. Because in NaOH there's 1, and then in trona there's going to be 3 of them. And so we know that X plus 3Y has to equal 0.5, because that's going to be our final concentration. And then for trona, you might think, oh, it's just going to be Y, right? Y HCO3 minus, because that's the only source of HCO3 minus that's coming from any of these. But this is where it gets a bit complicated, because as it turns out, HCO3 minus is going to react with NaOH at whatever chance it gets to produce whatever. And so you needed to know that. And so really 0.1 is not going to equal just Y, it's going to equal Y minus X, because X amount is going to get used up in this reaction. And so the amount left that we have is going to be Y minus X. And if we solve this system of equations, we're going to get that 4y equals 0.6, so y equals 0.15, and x equals 0.05. And so we're going to have 0.5, 0.05, sorry. In fact, I'll just show the answer. 0.05 moles of NaOH and 0.15 moles of trona. And those are the same answers that we got here. Um, and we did that by just setting the concentrations equal to X and Y, and then finding out the value using the final concentrations. And so I guess this is the difference between local questions and national questions. In national questions, you're required to have a more complete understanding, and so you needed to know that this reaction would occur in order to get the right value for trona. Last question, and thankfully it's not a calculation question. Um, as the concentration of an aqueous solution of sodium chloride increases from 1 molar to 2 molar, the values of which properties of the solution decrease? So let's try to imagine what that looks like. Let's say we have this box right here, and this box represents 1 liter. And let's say you have like this many particles is 1 mole. Or 1 molar, sorry. And over here you have another 1 liter box, and in this one you have double that. So in this one we had 5, and so in this one there's going to be 10. I think that's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and that's a 2 molar concentration box. And so we're asked to see which properties of the solution decrease. First of all, we have density, and density would not make sense. In order for density to increase, we would need less particles, but we have the complete opposite. We have more particles, meaning the density would actually go up, and since it doesn't decrease, I cannot be one of them. And then let's look at 2, freezing point. So this is basically asking us, is freezing point depression going to be more prevalent in the 2 molar solution? And that's going to be yes, because although we have in molar here, we can see that in molality, the number of the molality of this one right here is going to be less than the molality of this one right here. And that means that we're going to have more freezing point depression because the M value has gone up. So M has gone up, and so has change in TF. And since freezing point depression gets lower as molality goes up, that means that freezing point does go down if you change the concentration from 1 to 2. So only 2 is right here, and that is the answer. And that's it. We basically went through a local test and basically almost all of a national test. And that marks the end of Stoic. There's like a couple more things in Stoic, but they're really minimal things. They don't come up a lot. If you see things like things involving gases and whatnot, don't worry. We do get to that. They're not as common on this section of the test, but we do get to that later on, where it becomes more relevant in what we're learning. But other than that, that's all I have. Hope you enjoyed Stoic, and I hope you enjoyed this lesson. Hope you learned something, and I'll see you next time.